So in last class, we have discussed about a couple of the important signal conditioning blocks using operational amplifiers, like the different op-amp configurations, that filter characteristics, including low pass, band stop, right? And you must have received the that slides also, right? And uh, in last year. So in last class, just someone asked or someone told that this band stop, he was having some confusion, plus or minus. Statement I have written here, and from this example, it is clear to you that how just by adding these parallel connections of low pass and high pass will give you the band stop characteristic, right? So I hope that is clear to you. Okay. Okay, so today let us start with this ADC-DACO part, okay, which also will come under the signal conditioning blocks, right? So analog to digital conversion. So analog, so as you can understand that whatever this real world signal, if we consider, so like some temperature, pressure, right? So then you can have flow, different type of variables, speed, displacement. So those typically are analog signals which consist of continuous value, and also that you can see this is one that analog signal, and this is typically it can be some temperature, speed, pressure, like this. And analog signal means at each time instant we will be having the definite value for that particular signal, right? But when we will talk about our embedded system applications, so then typically we will deal with the digital signal, which is basically the discretely valued signal, like integers encoded in binary format. And typically if we look at some digital signal, so that means that is the discretized version or discrete form of the analog signal, right? And at so basically we discretized or sampled an analog signal in regular intervals, fine. And those interval values, we basically represent them using some typically binary representation, using 4-bit, 8-bit, 16-bit like of configurations, right? And that will give you the digital signal. Now, depending on our requirement, when we will deal with some embedded control system applications, then obviously that embedded systems has to interact with the real world or the physical world, where typically it needs to deal with the analog signal. But to make the analog signal compatible with the digital signal or the embedded system, we need to convert the analog signal into digital signal using the ADC or the analog to digital converter. Similarly, at the output end, when the digital signal is being processed inside the microcontroller, and after the processing is done, when after the processing we need to get back that signal, or we need to give some command to some actuator in the output, then again we might require to convert the digital signal into analog signal with the help of the DAC or the digital to analog converter, right? Now, typically, if you look at this block diagram where some physical variable we measure with the help of some sensor or transducer, which will give you the electrical analog signal, then you can pass it to some ADC, which will convert that analog signal into digital values, and that digital values will be processed inside our digital system or the microcontroller or the embedded system. And then after processing, we may require at the output end a DAC, which will convert that digital signal again back into the analog signal, and that analog signal will be capable to drive some actuator, and finally from the actuator we will get some control physical variable, right? Now, if we want to understand the analog to digital conversion, I hope that you have already studied these basics analog digital circuits in your basic electricals or some other courses. But just for the continuity purpose, so if you look at this, so here this is your analog signal, and you can see this is the continuous valued signal. Now if we want to convert it into digital, what we will do, we will discretize it. So discretize it, suppose along this axis we are discretizing it in some these intervals. So like we have this suppose typically this is the signal. So what we generally do, we will discretize it along this vertically, right? So discretize means at some regular interval, like at 1 second interval or 1.5 second interval and so on, right? And then after discretizing this, we will get these discrete values, right? Here only this couple of discrete values we will be getting. Here you can see the dots. Then again, if we want to convert it into digital, so what you have to do, you have to determine how many bits you want. Suppose if you want to use 4 bit representation, then what you can do, you have 4 bit means 0000 to 1111. So 0 to 15, these possible levels you can consider, right? And suppose, for example, if we consider the analog signal with the range of for example 0 to 7.5 volt, and then this 0.7.5 volt, if we want to correspond to this 0000 to 1111, so then what you will get, how many levels will be there between 0000 to 1111? 15 levels, is not it? And between 0 to 7.5 you have 7.5 volt. So then each level will correspond to how much? 7.5 volt divided by 15, so that will give you 0.5 volt. So here you can look at this table, where you can see that 0 volt should typically correspond to 0000, 0.5 volt will correspond to 0001, 1 volt will correspond to 0010. Likewise the 7.5 volt will correspond to 1111. So in that way, I can map this analog voltage signal into the corresponding digital signal using 4-bit representation, right? Now what we can do to look at this. So here, suppose this is the typically some analog signal, and we are discretizing along this this along its time axis. So T1, T2, T3, T4 interval, and then we have the levels in y-axis, like 1, 2, 3, 4. These are the typical levels. Fine. So what we can see, that here you can understand that between 0 and 0.5 we don't have any bit, because the minimum resolutions, if we consider 4-bit representation and the value of the analog signal maximum value is 7.5 volt, in that case you can minimum resolutions is 0.5 volt, right? You cannot measure 0.25 volt, is not it? So suppose if you have some value between 0 and 0.5, suppose here you have this analog signal where this is your 0 volt, suppose this is 0, this is your 0.2, this is something 0.5, like this. So 0 can be mapped with 0000, and this 0.5 can be mapped with 0001. But what about this 0.2? 0.2 has to be mapped either to this 0 level or this 0001 level, is not it? So here you can understand that if you consider 4-bit representation, then you can minimum measurement value possibility is 0.5 volt, right? But if you increase the bit size, suppose if instead of 4, if you use 5 bits, 5 bits, then how much levels you will be getting? 0000 to 11111, right? So that means 0 to 32, is not it? Or basically 0 to 31. So 30 levels will be there. In that case, the 7.5 volt, if we want to map, then what will be the typical resolutions? Instead of 0.5, it will be 0.25, is not it? So by that, you can easily understand, as you will increase your number of bits, your resolutions will improve and the accuracy will be improved. Why accuracy? Because here you can see this, if we consider 4-bit, then you can minimum 0.5 you can measure. If it is 0.2, then either it will be approximated to 0.5 or 0, right? But if you use 5 bits, then minimum 0.25 value even also you can measure correctly, right? So that's why as you will increase your bit, the resolutions or the accuracy will improve. But what is the disadvantage? Disadvantage will be the cost will improve, increase, or the this your computation time might increase, likewise, right? So there is trade-off. Now here, just as you can see, so this digital signal means that is discretized both along axis as well as the amplitude axis, is not it? So there are labels like 000000001. Those are the labels. Fine. So this is the basic concept about this analog, digital, their conversion and the interpretation. Is it okay? Any question? Please let me know if you have any question. Yeah. So now we will discuss the this interpretations of the ADC or the DAC and the DAC. Okay. So just first check out this ADC specification. So typically the ADC IC typically you can consider like this, where an 8-bit ADC block diagram has been shown, which typically includes the one V reference, one pin for V reference, another pin for ground. Then you can have one pin for the analog input. Then since it is 8-bit ADC, so you will be having 8 digital pins, which will give you the digital conversion of this analog signal. And then you can have some pin for start conversion as well as end of conversion like this. Okay. Now, as I told already explained in the last slide, so here the like bit versus resolutions or the step size is mentioned. So as I in the last example we have seen that if we consider this 4-bit, if we consider this 4-bit, so then what we told that your in case of here 8, 10, 12, 16 likewise it has been shown. So suppose if you consider 4-bit and if you consider this reference voltage is 5 volt, then for 4-bit how many steps will be there? 2 to the power this 4, so that means 16 steps. And we have seen, we can tell that 16 steps means each step will correspond to 5 by 16 voltage, isn't it? So something like your 0.31 volt around like this. Okay. But that means around 310 millivolt. But if you consider 8-bit, then that will correspond to 2 to the power 8 means 2 to the 256 steps or 256 levels, right? So then each level will correspond to how much voltage? If we consider 5 volt is the reference, so 5 by 256, that is 19.5 millivolt. If you increase the bit from 8 to 10, your step size will reduce further. Even if you consider 16-bit, then you are capable to reduce the step size further, that is 0.076 millivolt, that means 76 microvolt. So if you consider 16-bit representation and the reference voltage, if you consider 5 volt, then even the 76 microvolt resolutions you can achieve, or the accuracy you can achieve up to 76 microvolt, isn't it? So typically for ADC, what are the typical characteristics? Like resolutions, that means resolutions is defined from the bit size. So n bit resolutions, where n can be 8, 12, 10, 16, 24 like this. Higher resolutions ADCs will provide smaller step size, where step size is the smallest change that can be measured by an ADC, right? Then V reference is your input voltage, which is used for the reference, right? And then another characteristics or terminology is used for that conversion time. So conversion time, what does it mean? That how much time it requires to convert this analog signal into this 8-bit digital configuration, right? So in addition to resolutions, conversion time is another major factor. It is defined as the time it takes the ADC to convert the analog input into a digital number. The conversion time is dictated by the clock source connected to the ADC, in addition to the method used for data conversion and technology used in the fabrication of ADC chip like MOS, TTL. Those are the technology which is used to fabricate the ADCs, right? So additionally, you can have start conversion and end of conversion signal. So like if you enable this start conversion, then the ADC will start to convert this analog value into digital configuration or the digital data. Then similarly, you can have some EOC or end of conversion signal. You can enable or disable, or when the conversion is completed, then the EOC or the end of conversion will be enabled, or that will give you some signal that look, your conversion has been completed, right? And here one example has been shown that suppose Atmega 32 microcontroller already you are aware of. Now, if you want to connect this Atmega 32 microcontroller with some temperature sensor like LM35, so then what you can do? this microcontroller consists of inbuilt ADC, right? So what you can do, the LM35 typically it deals with, it includes 3 pins. One is for VCC, that is the supply voltage, another is for ground, and another pin corresponds to the that output of the temperature sensor, right? So what you can do, the output of the sensor that you can connect to the ADC0 pin of the Atmega32 microcontroller. What does it mean? This LM35 temperature sensor, it will give you some digital, it will give you some analog voltage output depending on your ambient temperature, and that voltage signal will be connected to ADC. So that means that voltage signal will be converted into digital this bits using the inbuilt ADC of the microcontroller, and then that digital data will be processed inside the microcontroller. Okay, so that is the so these are the typical characteristics or interfacing aspects of some sensor with your embedded system or the microcontroller. Is it okay so far? Any question? If you have any question, please let me know. Yeah. So just let us look at the some example of this this ADC. So some example of the ADC, let us look at. So this is the one example is called as a successive approximation ADC. So this is one type of ADC which is widely used. So as you can see in the last slide, that there are different type of ADCs are available depending on their technologies or depending on the techniques, how the analog signals are converted into digital signals. So there are different type of techniques are there, right? So what are the different type of ADCs are available? Like you can have ADCs like flash type ADC, flash ADC. You can have SA ADC. SA means this successive approximation, which we are going to discuss in detail, right? Then you can have some this dual slope integrator ADC, dual slope integration type ADC. Then you can have some sigma delta ADC, etc. So there are different types of ADCs are available depending on their this conversion techniques, right? So here just the representative purpose, we will discuss in detail about this SA type, that is the successive approximation type. What is the technique used here? How the conversion happens? How to and also later on you can understand that how to deal with the programming aspects or the interfacing aspects of ADC with respect to our microcontroller, right? So here let us look at the techniques or the methods of conversion for this successive approximation type ADC, right? So this is the typical that block diagram of your successive approximation type ADC, where the typical ADC you can understand, right? Where you have this analog input will be given as the input to the ADC, and it will give you digital D0, D1, D2, D7, likewise this digital bits as the output, right? So here what is done, it essentially consists of this ASH means one sample and hold circuit, one comparator, one SAR, that is the successive approximation register. You know about the register, right? Then it includes one DSC also, that is the digital to analog converter, right? And what we have this, what do we mean by this sample and hold? So sample and hold means you can understand that I have suppose some analog signal like this. So this I want to convert it into the corresponding digital. So first step is we have to discretize the signal. How to discretize it? We can use this sample and hold circuit. What is the logic of the sample and hold circuit? Here that simplest logic has been shown here. So this AI correspond to the analog input, this one, which we need to discretize, and AO correspond to the analog output, right? So here what it includes, typically just these are the some amplifier blocks has been shown, but the basics of the sample and hold is simply it consists of one switch and one capacitor typically, right? So what happens? This switch, switch can be implemented using some MOSFETs or some transistor based configurations, and then you have some storing capacitor. So what you can do, suppose this analog signal is coming here, then when the switch is off, that means it is disconnected, then this, you can consider this one as buffer. So same analog signal will come at this point, right? Now what you will do, the switching you will do at some regular interval. So what you will do, switch on off on off on off. Likewise, considering some particular frequency, you will make on and off like this, right? So on and off if you do, then what you will get, suppose this is your analog signal. Now on and off means what, this analog signal is coming here and that same analog signal is coming here. Now here is your switch. When the switch is closed, then that analog signal will be coming over here, and the capacitor will be charged to that particular value. And what we are doing, switching on and off. So suppose at this interval we are switching on, so that means this particular data has come over here. Now after some t1 interval again we are switching, then after t2 interval again we are switching, after t3 again we are switching like this. So then what we are getting, we will not get all the continuous data over here, rather we will get some discrete data at this point, fine. And then the capacitor, what it will do, it will store that charge. So basically if you look at the capacitor output, then what you will get, suppose here, just if we draw it big in some bigger way, so suppose you are switching in this interval like this, so then what you will get, this data will be stored at the capacitor, and until it will get the next sample data, it will hold that value. Then at this instant it is getting some new value, so then again it will go to that new value, then again it will hold that data. Then next value is like this or over here, so then it will come to this and it will like this. So likewise here, so if you just, how it will look like, so likewise this digital type of data or the discrete data you will get at this output, is not it? So that is the job of the sample and hold circuit, and its use is to discretize the analog signal which you want to convert into the digital bits, right? So that's why what we are doing, this V in, that is the input voltage which you want to convert it into digital, that we are feeding over here, and that will go to some sample and hold circuit, and here the discrete value will come over here, fine. And here we have the comparator. So you know the logic of the comparator. What logic? It will compare between this non-inverting terminal and inverting terminal, and if the non-inverting terminal value is more, then it will give you this plus VCC. If the inverting value is more, then it will give you minus VCC, right? So plus VCC minus VCC, that you can correspond to the logic high, logic low, like this, right? So 1 or 0 you can consider as the output of the comparator, fine. Then what you will get, this comparator output will go to this successive approximation register. What is the job of the successive approximation register? In this successive approximation register, initially, to whenever we want to convert some analog signal into digital signal, initially already some digital bits will be stored in the successive approximation register. Okay, so you know that how many this analog signal you want to convert it into how many bits, right? So you have already some predefined value that will be set at this successive approximation register, fine. And that successive approximation register value, the digital bits will go to some DAC. So inside the ADC, one DAC is also required. So DAC, what it will do, it will take that successive approximation register digital bits, and it will convert that digital bit into the analog signal, and that analog signal will be compared with our input signal, and then depending on which is more or which is less, either it will give you logic 1 or logic low, logic high or logic low, that means 1 or 0 output at this comparator output, fine. And depending on whether the value is 1 or 0, depending on that, in the successive approximation register, either the digital bits which is already stored there, either it will be increased or decreased, right? And how long this loop will continue? It will continue until this successive approximation register value or the corresponding digital bits matches with our V in. Till that point, the loop will continue, and finally, when these two will be equal, then that particular data which will be stored in the successive approximation register, that will be the converted digital bits, right? So let us that illustrate further. So what, suppose you want to convert some 5-volt signal, and suppose you want to use this 4 bits. You want to convert this digital bits, you want 4 bits should be there, right? Suppose 4 bits should be there. So that means 4 bit means the range will be 0000 to 1111, right? So for this example, what will be the initial value stored over this successive approximation register? For this example, it will start from the mid value. So what is the middle value between 0000 to 1111? The middle value is 1000, right? So typically, just for the simplicity, if you consider 0 volt 0000 correspond to 0 volt, and 1111 correspond to 15 volt, right? So then this 1000 correspond to how much volt? 8 volt, just for simplicity, right? So now what it will do, suppose this V in is, for example, 5 volt. Suppose V in is 5 volt. Okay, so 5 volt, it will be discretized here, right? And here how many volt is stored? Initially 8 volt is stored, right? So 1000 will be stored, 100 will come here, 100 will be converted it through the DAC, and the corresponding voltage will be 8 volt, right? So this 8 volt and 5 volt will be compared, and it can see 8 volt is more. Okay, so here you will get logic 1, is not it? When logic 1 will be there, then it will understand that the whatever successive approximation register value is stored, that is higher than the input voltage, is not it? Because here it is 8 volt, here it is 5 volt. So 8 volt is higher than the 5 volt. That can be understood by the comparator output. If comparator output is high, then it will understand that 1000 value, what is already stored here, that is higher than my input voltage. So what it will do, it will decrease that, it will decrement the successive approximation register. So initially the stored value is 1000. It will, what will be the, when it will see here the signal is 1, so then this 1000 will be converted into the 0100, right? So 0100, what it will do, it will make the MSB 1 to 0, and the next MSB it will convert from 0 to 1, right? Again 0100 correspond to how much volt for this example? Simply 4 volt. So again this 4 volt will be coming here. 4 volt will be compared with 5 volt. 4 volt and 5 volt comparison, what it will give, this 5 volt is more than the 4 volt. So then this, so instead of 8 volt, then in the next step 4 volt will come, and 4 volt 5 volt will be compared. It will see this negative input is more, so then 1 will be so here you will get 0. When you will get 0 over here, then this this will understand that whatever 0100 is stored here, that corresponding analog value is lesser than my analog input. So what it will do next, the 0100, it has to increase further. So what it will do, 0110, right? So 0110, that will correspond to how much? 6 volt. So then in the next step you will get 6 volt. So 6 volt and 5 volt will be compared, and here this 6 volt is more, so here you will, instead of 0 will get 1 over here. So then it can see that 1 it has got, that means whatever 0110 is stored here, that is more than my analog input, so it will decrement it. So what will be the corresponding decrement? 0101, because this is the, in this logic the increment and decrement happens. The increment and decrement does not happen serially 1 2 3 4 like this, rather it will consider the MSB and the next MSB like this, right? So in the next step we will get 0101, and 0101 correspond to how much volt? 5 volt. then it will see 5 volt match. So then it will stop here, and from this successive approximation register, this DA, D1, D2, D3, here you will get 0, 1, 0, 1. That is the output. That is the corresponding digital conversion of this 5 volt analog signal, right? And here you can see typically for this case how many steps is required. In one step, 1 0 0 0 2 0 1 0 0, next step this one, next step this one, 1 2 3 steps are required over here, fine. So we can see that if I have n bit ADC, n bit successive approximation register ADC, then whatever be the analog signal, we need maximum n number of steps. So here we have 4 bits, so maximum 4 steps. And in this example, we have seen in 3 steps itself, it is successfully converting my analog signal into the corresponding digital value. So maximum step requirement is for n bit and conversion, it requires maximum n steps. Okay, is it clear? The concept of successive approximation register, is it clear to everyone?
Sir, can you just briefly explain the each step?
Which one?
I mean that 3 steps, that 1 0 0 0 to 0 1 0 0.
Okay.
That yes.
Okay. So what I told, that suppose 5 volt is my analog signal which I want to convert into corresponding digital bits. Okay, the question is clear, right? Now how this will work? As I told, in this successive approximation type ADC, there is a successive approximation register where already some predefined digital bits are stored. And if I consider 4-bit ADC, then it will store 1 0 0 0. If it is 5-bit ADC, then what would be the value? 1 0 0 0 0. So this half value it typically stores, right? So that is the predefined value, predefined initial value, you can say. Okay. So how it will work? 1 0 0 0. Typically, for simplicity, here I have considered this 0 0 0 0 to 1 1 1 1, that correspond to 0 volt to 15 volt. Okay, that is fine. So from that logic, 1 0 0 0 correspond to how much volt? 8 volt. Okay. So in this successive approximation register, 1 0 0 0 is stored. So 1 0 0 0 will come over here. Then it will go to the DAC. DAC will convert that 1 0 0 0 signal, and what will be the corresponding DAC output? It will be 8 volt. Okay. And in the analog input, what voltage is fixed here? 5 volt. So this 8 volt and 5 volt will be compared here. Okay. It will see 8 and 5. If you compare, 8, that is the positive input, that is more than the negative input. So here logic high or 1 will be the comparator output. When the comparator output is 1, it means that whatever predefined value is set over here, that value is more than my analog signal. So it has to decrease. And how the decrement happens? 1 0 0 0 0. The next decrement is not 0 1 1 1. Not serially. The decrement or increment does not happen serially. Rather, what logic is followed over here? While decrementing, it will see this MSB, it will start from the MSB. Here it can see this MSB is high. So it will immediately make that MSB low. And the next MSB it will make from 0 to 1. So 1 0 0 0, the next step will be 0 1 0 0. Okay. And when it will see this 0 1 0 0, that corresponds to 4 volt, that is less than my analog signal. So then it has to increment. And how the increment will happen? The 0 1 0 0, the next increment will not be 0 1 0 1. Rather, it will see this MSB is 0, so it will keep this as 0. This is 1, it will keep this as 1. The next MSB is 0, it will make it 1, and next is 0. So likewise, the increment and decrement happens. Is it clear or any doubts?
Okay, sir. Thank you.
Okay. Okay. Similarly,
Sir,
I have other.
Sir,
Yeah,
how
go
did
ahead.
the last decrement happen? Because in previous class there was a 6 and the input was 5 volt. Then so 6 is greater than 5.
In previous class, miss?
No, I said in
Here you are
here.
saying. Okay.
Here the before the last case there was that from the DAC it was coming 6 volt and the input is 5 volt. So 6 is greater than 5. So after comparator, the output will be 1.
No. Yes. Yeah.
So then the MSB is 1 and there is another one. So but the first one is not changing, the second one is changing.
Okay.
How?
Yeah. See. So here 0, 1, 1, 0 that correspond to 6 volt, and we have to decrement it, is not it? Because here we have got 1, so that means this value is higher than the analog, so it has to decrement. And decrement means what? This is 0. This is the next MS. So since in the previous case also this MSB works fine, so it will not lower this MSB. This MSB will be, so 0, 1 will be as it is. Rather, what it will do, the next MSB, it will see this is 1, so this you will make it 0, right? And you can say that here this 1 is 0, and you can say that here one more here you have this 0 over here, so this MSB will be converted to the from 1 to 0. Okay, and then this the next MSB, or that is the LSB, it was 0. So how it will decrement? So you can say that if 1 bit decrement, then it will again go back to 0, 1, 0, 0. I think you are saying like this. So 0, 1, 0, 0, but it has already seen 0, 1, 0, 0 does not work, that is less than this. So instead of 0, 1, 0, 0, it will make this MSB to LSB, and this this MSB 1 from 0, and this one from 0 to 1 likewise. So that is the logic which is followed for this incremental or decremental case. Okay.
Yes, sir. Okay.
So there are other type of ADCs like flash ADC, and here conversion time is very important factor. So you can see n number of steps are required, right? And one step corresponds to how much time? You can see here one clock is there, right? Here one clock is there, and you know this clock is having some typical frequency. Suppose if you have 1 megahertz clock, so 1 megahertz clock means what is the time period? 1 microsecond, is not it? So each clock duration is 1 microsecond. Okay, and each step correspond to each clock. So n step means how much clock? N number of clock. So if for this example, if the clock frequency is 1 megahertz, the corresponding time is 1 microsecond. So then my conversion time will be maximum n microsecond. If it is 3 step, then 3 microsecond. 4 step, this then 4 microsecond. If the clock frequency is 1 megahertz, right? So in that way, we can calculate the conversion time. And while programming aspects, you need to be aware of the conversion time as well. Okay, is it okay? So this is just one representative ADC type which is widely used. So that's why we have discussed in detail about the successive approximation. Other types are also there, like I mentioned, and depending on the requirement, you can choose different types. But as this successive approximation is the most common, so that's why we have emphasized more on this. Okay. Now, let us look at some example of the practical signal conditioning circuit. Achha, so here, can you see the title, or it is not visible?
Not visible, sir. It is not visible.
Yeah. Now it is okay, right? Yeah. Yeah. So now we will see. So we have understood about the amplifiers, filters, ADCs, etc. Right? Now let us look at a practical signal conditioning circuit to interface with the microcontroller. Okay. So earlier, so we have understood, we have discussed about this thermistor temperature sensor. You remember, right? So what is our problem, or what is the question now? That I want to interface a thermistor. I have a thermistor temperature sensor. I want to interface a thermistor with the microcontroller. Okay. So what are the practical considerations I need to take care of? Okay. So here is just to give you some representative idea. We are going to discuss this example. So you remember this thermistor is very highly sensitive but highly nonlinear, and typically it follows this exponential nonlinearity curve. Fine. And here is some typical thermistor data sheet where temperature versus resistance is shown over here. Okay. So this is one temperature versus resistance minus 50 degree. The resistance ratio is 39. Likewise here minus 50 to 110 degree. The corresponding resistance ratio is shown. Resistance ratio means what is meant by R by R25. That means with respect to the 25 degree centigrade temperature, with respect to this 25 degree centigrade, the corresponding resistance is R25, and at this 110 degree centigrade, the resistance is R. So that in that way the ratio is expressed over here. Okay. Now when I want to design some signal conditioning circuits for the thermistor, then what I have to do? Thermistor is a resistive type device, is not it? So with respect to the temperature, its resistance changes or resistance decreases, right? So if I want to convert that resistance change into voltage change, what I have to do? I can simply use some voltage divider circuit. You know, this voltage divider, this is your voltage divider circuit, right? So this is the simple voltage divider circuit where here this configuration is like this. Okay. So here you have this V reference, here you have this R1 resistor, and here you have this R thermistor. Fine. And for this, from this, I am taking the voltage output. Now, this voltage output will be some analog voltage signal. That voltage signal, what is our requirement? I want to connect it to the microcontroller. And I have to connect it to the ADC, is not it? Because this is the analog voltage signal we will get from here, and that analog voltage signal has to be connected to some ADC so that I will get the digital bits which will be processed by the microcontroller, right? So typically this is the voltage divider we can use. And in case of thermistor, there one problem is there, that is called as the self-heating effect. What this self-heating effect means? Now when I will connect this thermistor in this voltage divider configuration, then easily you can understand, here I have some voltage, here I have some resistance. So some V by R, that amount of current will pass through this circuit, is not it? Now you are aware of the Joule's heating effect. So when some current I will pass through the some resistance R, then I square RT, that Joule's heating effect will be there. And due to that Joule's heating effect, some temperature will be developed across the thermistor, is not it? And what is the job of the thermistor? Thermistor's job is to measure the temperature. So when it is exposed to some temperature, and because of that temperature, it has achieved certain resistance value. Now I want to convert that resistance change into voltage change. In order to do that, I have used this voltage divider. But because of this voltage divider, some current is flowing through the thermistor, and the additional heat is being developed across the thermistor. So suppose it is exposed to 100 degree centigrade, and because of the 100 degree centigrade, it is showing suppose 5 kilo ohm. Now because of the current, some additional temperature will be there, and instead of 5 kilo ohm, it may show 5.2 kilo ohm. Where from that extra 0.2 is coming? That is coming because of the Joule's heating effect. That 0.2 does not correspond to some ambient temperature. That is happening because of the current flow, right? And obviously that is not our desire, because I don't want that because of some current the temperature should change. I want only because of the ambient temperature, its temperature should change and its resistance should change. But because of the current, if it changes, so that is not desired. That is called as the self-heating effect. Okay. And how can we reduce the self-heating effect? I can use some high value of R1 resistor, so that, you know, Ohm's law, V by R is I. So by considering some high resistance value, I can reduce the current which is passing through this thermistor, so that due to that current, the heat effect will be less. So that is just one this practical concepts I discussed. so that you can understand that when I will be actually designing in the field about some temperature control system, or I want to interface some temperature sensor with the microcontroller, then what are the different things I need to consider, right? Okay, so by adjusting or by choosing some high resistance value, you can reduce the self-heating effect. That is fine. Now, what is my main job or main goal? I want to connect this thermistor with the microcontroller. So then what I have to do? Just look at this circuits further. So suppose this is our circuit and this is a simple buffer is there. So buffer will just pass whatever value is coming over at this point. Suppose here V1 voltage is coming, the same V1 will come here, and that I want to connect to the ADC of the microcontroller, right? Now here just one example. Suppose I have this temperature versus resistance versus voltage data for this circuit, where suppose 0 degree centigrade temperature, the resistance of thermistor is 28 kilo ohm and the corresponding V1 voltage is 1.84. So how can I calculate this voltage? Simply this reference voltage I am considering 2.5 volt for this example, and 2.5 into this RTH divided by RTH plus R1, that is the voltage divider equation, right? And using these equations I can simply calculate what is the voltage over here. Okay, now suppose a problem is given to you that we want to measure the temperature between 10 and 40 degrees centigrade with an accuracy of at least 3 ADC steps per degree. Please that read this carefully and listen the statements carefully. Okay, so what is told? Suppose this data sheet is given to you, temperature versus resistance of the thermistor, and using this voltage divider circuit you have calculated for different temperature what will be the resistance and what will be the corresponding voltage V1. Now you want to design some temperature measurement system which is capable to measure the temperature between 10 degree to 40 degree. So what is your range you want? Your range is 10 degree to 40 degree. That is your measurement range. And for this 10 degree, what is your voltage? For 10 degree, the voltage is 1.61 volt, and for 40 degree, the voltage is 0.976 volt. Okay. Now, what is your requirement? You want an accuracy of at least 3 ADC steps per degree. That means when you will connect this voltage divider output to the ADC, then each degree centigrade correspond to 3 ADC steps. So what does it mean? Suppose you have 8-bit ADC. You have suppose 8-bit ADC. So 8-bit ADC means 4, 5, 6, 7, 8. This is the minimum value of the 8-bit ADC. And what is the next level? Next level will be 5, 6, 7, 8. And next will be 0, 0, 3, 4, 5, 6, 7, 8. Right? So likewise, the last will be 4, 5, 6, 7, 8. So these are the corresponding this ADC output, right? Because we are considering here 8-bit ADC we are considering. We are considering 8-bit ADC, and the reference voltage of the ADC we are considering 5 volt. Okay. So what is our requirement? I want that each degree centigrade correspond to 3 ADC steps. Okay. So that means here from here to here one step, here to here another step, and then next value will be 4, 5, 6, 7, 8. So I want, suppose if this correspond to 0 degree centigrade, then 1, 2, 3. This should correspond to 1 degree centigrade. So that 1 degree centigrade correspond to 3 ADC steps or 3 ADC levels. Okay, that is my requirement. Now let us look at the datasheet and try to see whether I can satisfy this criteria or not. So let us look at 10 degree centigrade, what is the voltage? 10 degree centigrade, the voltage is 1.61 volt. Okay. So if I want to convert this analog voltage 1.61 into the corresponding digital value, what I will get? You know, this 5 volt is the reference. So this 1111 correspond to 5 volt and this correspond to 0 volt. Okay. So since if I have 8 bit, then how many levels will be there? 2 to the power 8 means 256. Okay. So each step correspond to how much voltage? 5 by 256. Is not it? So in the other way, if I say 256 level correspond to 5 volt, so one level correspond to 5 by 256. Okay. So here I can see, here I have the, what is the voltage? 1.6 volt. Okay. So 1.6 volt should correspond to what is the digital bits? It will be simply 1.61. What is my reference voltage? 5 volt. That into 256. Isn't it? So 256 level correspond to 5 volt. Or in the other way, 5 volt correspond to 256. So in the other way, so instead of this, I can say this 5 volt correspond to 256 digital bits. 1 volt correspond to 256 by 5. So 1.61 volt. So 1.61 volt will correspond to this 1.61 by 5 into 256, right? So 1.61 by 5 into 256, that is the digital value is coming as 82. Similarly, for 40 degrees centigrade, the value is 0.976. That will correspond to 49 digital bits or digital value. Okay. Now let us look at whether this requirement accuracy of at least 3 ADC steps per degree is achieved or not. Let us take the difference. 82 minus 49, that corresponds to 33, and the temperature 40 minus 10 corresponds to 30 degrees centigrade. If you divide 33 divided by 30, that means 1.1 ADC steps per degree. Right? So based on this data, or based on this simple voltage divider circuit, if I calculate the corresponding digital conversion for this ADC, then I can see that 1 degree centigrade correspond to 1.1 ADC steps. But what is my requirement? My requirement is 3 ADC steps per degree. So what I am getting, that is lesser than my requirement. Okay. So if I want to achieve this accuracy, then I have to do some signal conditioning on this circuit, and we have to scale the output with respect to the ADC value. So that is the requirement of scaling, and that's why we need some additional signal conditioning circuits in order to achieve these specifications or meet the criteria. That suppose a problem is given to you that you want to design some temperature measurement system using embedded controller. Digital bits, and you can see that if you simply convert them, then 1 degree centigrade temperature correspond 1.1 ADC step. But my requirement is 3 ADC steps per degree, which I am not able to get. So in order to get this 3 ADC steps per degree, we need to add some additional circuits, and that circuits will typically look like this, where I need this voltage divider, then we need some signal conditioning circuits using op-amp, and this op-amp will do some purpose. So this op-amp output is typically like this. So this output we can get from these two equations. So basically we can apply some KCL over here. So you know this voltage you can calculate. This voltage is V1 and same V1. So here this V1 and V2 will be equal. So here if you put your nodal analysis, so then you can derive this expression. So please try to derive this expression, and by deriving this expression we are getting some V0 output, and V0 output, what type of output? The actual V1 that is getting amplified with this factor, as well as some subtraction is also happening. So that means some amplification is happening, as well as some level shifting is also happening, and this is essential to meet this specification. So I mean to highlight that to achieve the desired purpose or desired specification, we have no other alternatives than using some dedicated signal conditioning circuits. So that is the point what I want to highlight over here. So is the concept clear, or anyone is facing some difficulties to understand? Please let me know. Is it okay for all? Any question? Any question? Okay. So here that I want to highlight. So using these circuits, I can that amplify the voltage as well as level shift the voltage so that I can achieve the specification. So the details I am not showing here. If someone is interested, so please let me know so I can discuss further. So otherwise, this is the concept what I want to highlight here. Okay. Okay. If it is fine, so then we will discuss about the DAC. So that is the counterpart of ADC or the opposite role of the ADC. So in ADC, we convert the analog signal into digital signal. In DAC, we convert the digital signal into analog signal. So typically, this is the digital IC's block diagram, right? Like digital in DAC, also we need some reference voltage. Here, the input will be the digital bits and output will be the analog output. Okay. And typically, we have different type of DAC. So out of those, one is known as the binary weighted registers. So what is this binary weighted registers? Here also we use some op-amp block, operational amplifier, as we have discussed earlier. And here what we have, like B1, B2, Bn, these are the digital bits which I want to convert into the corresponding analog output. Okay. So this input will be these digital bits and output will be this voltage. This will be the analog voltage, which will be the converted value of these digital bits. Okay. How this binary weighted register work? So you know this. Suppose if I have some digital bits like 1 0 1 1. So what is the corresponding this decimal value? How do we do that? This 1 that we multiply with 2 to the power 3, right? This 0 we multiplied with 2 to the power 2. This one we multiplied with 2 to the power 1. This one we multiplied with 2 to the power 0, right? We multiply and then add. And by doing that, we get 11 as the binary value, that decimal value, is not it? So basically, factor of power of 2 is getting multiplied with the subsequent adjacent bit. So here how the concept is there, this multiplying with factor of 2, that is implemented using different type of register values. How the register values are chosen? Like R, 2R, 4R, 8R, 16R, likewise the values are chosen. Okay. So suppose if I want to convert this n number of bits, 1 2 3 4 n, so then maximum resistance value will be 2 to the power n minus 1 into R. Okay. So how it works? Suppose you can see here this operational amplifier, this non-inverting terminal is grounded and inverting terminal is connected to those bits, digital bits, and digital bits can be either 0 or 1, is not it? So when this S1, S2, S3, S4, these are the switches are there. So if the digital bit is 0, then this S1 will be grounded. If it is 1, then S1 will be connected to this terminal. Similarly, S2, when it is 0, then it will be connected to ground. If it is 1, then it will be connected to the op-amp. Okay. So in this way, what is the current flowing across this one? Suppose if this is connected, then the current flowing in this branch will be Vref by R. If this one is connected here, so then the current flowing across this will be Vref by 2R. When this one will be connected here, so Vref by 4R. So likewise, those currents will be flowing over here. And this will be simply acting as the adder or summer. So what is the total current? Total current I0, that will be simply Vref by R into B1. B1 is the digital bits. If B1 is 0, then it will be 0. If it is 1, then it will be Vref by R plus Vref by 2R into B2 plus Vref by 2 to the power n minus R into n minus 1 into R into Bn. Okay. This is the current I0. And then if this current passes through the feedback resistor, and if we choose Rf equals to R by 2, if Rf equals to R by 2, if we choose, then simply your output voltage will be how much? Minus, this is inverting amplifier. So minus I naught into RF, and I naught means what? I naught means this combination. Okay. So if you consider RF equals to R by 2, then what is the voltage output you will be getting? Voltage output you will be simply getting minus of this I0 into RF. So basically this Vref by R into R by 2 into B1 plus Vref by 2R into R by 2 into B2 dot like this. So that correspond to how much? So this will correspond to minus of Vref by 2 into V1 plus Vref by 4 into B2 dot like this. Okay. So essentially the example what I told, that 1011, how it is, how we convert the digital into the corresponding decimal value, multiplying with this 2 to the power some factor 0 1 2 3 like this and adding them. Similar concept is happening here, right? Because by 2 by 4 by 8 likewise. So in this way the digital bits is getting converted into analog signal with the help of this binary weighted register. And why we call binary weighted registers? Because the resistance you have to choose in binary form, like R, 2R, 4R, 8R, that means 2R, 2 to the power 2R, 2 to the power 3R, 2 to the power 4R, likewise. Okay. So this DAC is the simplest type, but the main disadvantage of this DAC is that we need lot of registers in order to design this. Because if R is 1 kilo ohm, then we need 1 kilo ohm, 2 kilo ohm, 4 kilo ohm, 8 kilo ohm. Likewise, as many number of bit will increase, as many number of different register values you will need. Right? So that is the problem over here. So to address this problem, we have another type of DAC which is known as the R2R ladder network, where we use only these two type of resistance is required, R and 2R. So only two resistance values. Suppose if I choose R equals to 1 kilo ohm, then 2R equals to 2 kilo ohm. So only these two type of resistors with multiple number is required. And here what is the concept? Here concept is like, suppose just the that R, that 2R, 4R, 8R, those are replaced by R2R in this way. R2R ladder concept it is told as. Here also this B1, B2 dot Bn, these are the digital bits which I want to convert into analog data. And here how it works, suppose if you consider this is grounded, if you consider this one is grounded, so then what is the, if you look at this from here, 2R and 2R, what is the equivalent of 2R and 2R? Equivalent is R. Then that R and this R, here we have some R, and R getting added. So here again 2R will be there. 2R and 2R parallel, equivalent will be R. R and R getting added. So that will give you 2R. So likewise, effectively that R2R, that type of concept is there. And here this I is connected to the op-amp. So op-amp plus is grounded. And here we have the feedback resistors. Here we have the voltage output. Fine. So this I0, we will get this I1 plus I2 plus I3 in that format. And here we will, that current will pass through this one, and V0 is again equals to minus I0 into RF. And from here we will get the digital, that analog signal which will correspond to the digital bits of the B1, B2 dot Bn in this way. Okay. So this is the another type of DAC. Is it okay so far to all, or any question? Any question? No question?
Sir, in the last one, I mean, how the that two multiplication is going on?
Yeah. So if you that want to that see the details of this A, that here you can see so here you can see this. Suppose if we consider this 4-bit R2R ladder network, and here this here you can see this is just represented in some another way, but the same theory. So here this R2R, that concept, and 2R, 2R, the equivalent is R plus R, 2R, 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 R. So effectively, this V1, V2, V3, whatever voltage is generated over here, that is the fraction version of this V-ref. So in the previous case for binary weighted register, our VREF by 2 or VREF by 8 or likewise the thing was happening. So VREF was fixed. But in this case, the VREF itself is getting changed to VREF by 2, VREF by 4, VREF by 8 like this, based on this. Okay. So here V3 will be VREF by 8, V2 will be VREF by 4, likewise. So that's why we don't need R2 or 4 or 8 or like this. Rather, only R and 2 are same. This V1 and V2, V3, they are getting changed accordingly to this 2 to the power format. So that's why we don't need dedicated R to that different values of register. Rather, we need this configuration so that the VREF itself, effective VREF itself is getting changed for different bits in this binary fashion. Is the concept okay?
Yes, sir. It is
Yeah.
fine.
So that this I will share. So okay. Okay, just 2 minutes we will wrap up. So just so here what we can see this we have understood about this analog to digital conversion and then digital to analog conversion as well, fine. And then but in this during these conversions we can get some sort of error. How the error will we will get, as I you remember we told that depending on how much bit, suppose this that example what I told, that 7.5 volt, if that will be represented with 0 0 0 0 to 1 1 1 1, so then what we told that each level, that each step, so one step correspond to how much volt we have seen 0.5 volt. So here in between, if in between 0 and 0.5, if you have some data, you have to approximate it either 0 volt or 0.5 volt. So in that way the error is coming, and that error is called as the quantization error. So here you can see this is the red one is the analog signal, and when we are converting into digital, then this type of staircase things we are getting, right? And those each staircase correspond to each level. Now suppose in this case here if we have some in between here, if you have some digital that some this value if I want to get, I will not get the exact value. Rather, this either I have to approximate to 101 or 100. So in that way, the quantization error is coming. Now this one, you just you look at this portion, and this portion, if I just write represent it in this form, so then simply you can see that this middle one dot line correspond to the dotted line, and these staircase things correspond to this one, right? So basically the error is coming, and what will be the error you will be getting, and this one if you just rotate at 45-degree angle, so that you can write it in horizontal way, and it will look like this type of staircase arrangement, right? So here this this difference correspond to what? One level change. One level change means 0 0 0 0 to 0 0 0 1. That is one step change or one level change. That correspond to one LSB, is not it? So if you calculate, the RMS error will be this q by root 12. So please derive that. If you have this type of triangular concept, and this triangular is happening because of this error which is coming due to this discretization or quantization, and if I consider this LSB as q, so error will be q by root 12. That will come from the RMS concept. So please derive that and consider as your homework. Okay, so this is about the quantization error in sampling. And just sampling means you have already understood that sampling, suppose you have some analog signal, this sinusoidal signal, if you sampling means just the discretizing with some discrete values, so that we can get this discrete values. And why do we need to discretize it? To convert it into digital form, right? And at which frequency we will discretize? Suppose if I have am I audible? Am I audible?
Yes, sir.
Okay. So during this discretization, what type of sampling frequency I will choose, that will matter a lot. So that we will discuss in the next tomorrow's class, and then we will discuss some other points, including the actuators or the different type of numerical representation concept, and then we will possibly try to conclude my part on tomorrow's class. Okay. So with this, I am concluding for today. And as I told on Monday, so basically initially we plan to conduct two tests. So one tomorrow from my module 8, and then from rest of the module another test on next Friday. But instead of that, we will just combiningly take the test. That means next week Professor Somnath will take the classes, and next Friday mostly we will conduct a combined test on the rest of the portion. Okay. So tomorrow the class will be held as usual. So please that prepare yourselves in that way. Okay. And I may give some couple of few assignments as well, which you will submit in the next week. So with by that we will conclude. So any questions so far? If you have any question, please
So
let me
there will
know.
be last test, right? In the next week. This will be the last test.
Hopefully. So because next Friday that is the last class, and mostly next Friday itself we will conduct a test from our rest of the part.
Okay.
Okay.